Have you ever stopped to think about something as simple as a pipe? I mean, how do engineers decide how big it should be? It seems so basic, right? Just a tube to get something from point A to point B. But, as we're about to see, that simple tube is actually hiding an incredible puzzle. We're talking physics, money, safety, all wrapped up in one. So yeah, let's get into it. And that really is the million-dollar question, isn't it? How big does a pipe actually need to be? For a process engineer, this isn't just a one-off question. They're making this call over and over and over again on any given project. And it doesn't matter what's flowing through it, natural gas, water, you name it, getting that diameter right is absolutely critical. Because if you get it wrong, oh boy, the consequences are huge. It's what we call the Goldilocks problem. If you go too small, you're in for a world of hurt. You're fighting all this friction, which means your energy bill for the pumps goes through the roof. Plus, the fluid's moving so fast, it's basically sandblasting the pipe from the inside out. Not good. But then if you go too big, well, you've just spent a fortune on steel you didn't need. And for some things, like slurries, if the flow is too lazy, all the solids just drop out and clog everything up. It's gotta be just right. So what this all comes down to, really, is a trade-off. It's a balancing act. On one hand, you've got the speed of the fluid, and on the other, you've got the energy you're losing just to push it along. The whole job is to find that sweet spot between the two. You nail that balance, and you've got a system that's efficient, safe, and doesn't break the bank. All right, so let's tackle that first piece of the puzzle, speed. The easiest way to think about this is like a speed limit on a highway. You want to get where you're going fast, sure, but if you go too fast, things start to break down.
In the world of piping, this is called the erosion velocity. It's the point where the fluid is moving so fast that it literally starts to eat away at the inside of the pipe. All that kinetic energy starts wearing down the pipe walls, the elbows, you name it. And over years of operation, that leads to leaks and failures. All the stuff you really, really want to avoid.
So how do engineers figure out this speed limit? Well, they're not just guessing. They use proven tools, like this formula right here from the American Petroleum Institute. Now don't get bogged down in the math. The key takeaway is that the top speed, that V, is all tied to the density of the fluid. Basically, the heavier or denser the stuff you're moving, the slower you have to go to keep things from wearing out. Okay, so staying under the speed limit is one thing, but that's only half the story. Now we've got to talk about the other side of that balancing act, the energy cost. I like to think of it as an energy toll. For every single foot of pipe you push that fluid through, you are paying a price. And this quote just nails it. It really does come down to what you can afford to lose. See, all that friction inside the pipe causes the pressure to drop. To make up for that lost pressure, you need a pump or a compressor working hard at the beginning of the line. And that costs money. Real dollars every hour, every day. So the engineer's real question is, how much pressure, and therefore how much money, are we willing to just let disappear into friction? This loss of energy is what we call pressure drop. And honestly, the perfect analogy is trying to drink a really thick milkshake through one of those tiny coffee stirrers. It's a ton of work, right? But if you get a proper wide straw, it's easy. It is the exact same thing with pipes. A smaller pipe means more friction, a huge pressure drop, and that means you need a bigger, more expensive pump to do the job. So to keep this under control, engineers have these rules of thumb for how much pressure drop is okay. A pretty common target for a line coming out of a pump might be something like losing half a bar of pressure for every 100 meters of pipe. It's a guideline that helps make sure your energy costs stay sane, but you're also not building a ridiculously oversized, expensive pipeline. It's all about finding that economic sweet spot. All right, so we've got our two big rules. Don't go too fast and don't lose too much pressure. Simple enough, right? Well, this is where things get really interesting, because the game completely changes depending on what's actually inside the pipe. And it's wild how different fluids can create totally opposite challenges. With liquids going into a pump, you have to keep the pressure high enough to prevent something called cavitation. That's where the liquid literally boils inside the pump and destroys it. With gases, they expand as the pressure drops, so you have to plan for that. With slurries, you have the opposite problem of erosion. You have to keep the speed up so the solids don't settle and clog the line. And then you have these really unique cases, like gravity flow lines. For these, the whole goal is what's called self-venting. You want the liquid to flow smoothly, not glug like a water bottle turned upside down. To do that, you use something called the Froude number to make sure the flow is slow enough for any trapped air bubbles to rise up and escape against the flow. This prevents vapor locking, but it means these drain lines often have to be way, way bigger than a pressurized pipe carrying the same amount of liquid. It's a completely different design philosophy.
And this right here is a perfect visual of why this matters so much. This is a pump performance curve. That sweet spot right in the middle? That's the pump's happy place, its best efficiency point. It's running smooth, it's efficient, but if you mess up the pipe sizing on the suction side, you can literally starve the pump of fluid, and that forces it to operate way out here on the edge of the curve. It starts to vibrate, it wastes a ton of energy, and eventually it'll just tear itself apart. It's amazing, isn't it? A simple pipe can directly affect a multi-million-dollar piece of machinery.
So you've got all these competing factors, right? Speed, pressure, what kind of fluid it is. How in the world do engineers land on a final answer? Well, it's this really cool mix of old school experience and cutting-edge science. The art part of it usually starts right here, with these rules of thumb. These have been built up over decades of just seeing what works. And you can see right away the job of the pipe completely changes the starting point. A pipe feeding a pump, you keep that flow nice and slow, maybe 1 meter per second, to keep the pump safe. But a gas line, you can let that fly much, much faster. These are the gut checks, the starting points that get an engineer into the right neighborhood. But today, that art gets backed up with some very serious science. Engineers take those ballpark numbers and feed them into incredibly powerful software. These programs basically create a digital clone of the whole piping system. They can model every single pump, every valve, every bend, and calculate exactly what the pressures and speeds will be. This means they can run tons of what-if scenarios to find the absolute best solution before anyone even thinks about cutting a piece of steel. And really, that brings us to the final, ultimate goal. Because when it's all said and done, the best pipe size isn't just a physics problem, it's an economics problem. The perfect design is the one that finds the equilibrium between the upfront cost of the pipe itself and the long-term cost of the energy to push fluid through it. You know, spending a bit more today on a slightly bigger pipe could end up saving a company millions in energy bills down the road. That's the real puzzle they're trying to solve.
So yeah, that simple pipe, turns out it's not so simple after all. In a way, it's a perfect little snapshot of what engineering is all about, finding that perfect, optimized balance between all these competing forces. It really makes you look around and wonder, what other simple objects in our world are hiding that same kind of incredible complexity?